Okie dokie. Good morning, chemists. We'll get started now. So we all took midterm 2, the majority of us yesterday. So we can anticipate that grades for those exams probably will not come until at the earliest end of this week, like on Friday, but most likely early of next week on Monday or Tuesday. And so you'll receive your grades first as soon as we're ready to release them. And then after all of your classmates have taken the alternative exam, we will release your exam responses after that. So that'll probably happen mid of next week. So yeah, that's what to expect. I'm very happy about the average that we had in our class. So I'll share that with you when I'm allowed to. So let's continue on with chapter 5. I'll remind you that midterm 3, which will be here in about 2 or 3 weeks or something, will cover chapters 5 and 6. I anticipate we will finish chapter 5, not today, but on Thursday. All right. So chapter 5 is about energy of chemical reactions, and I have a couple examples, demos of energy of reactions. We'll do the luminol, the glowy reaction again, because we liked that last time. We'll do that one again. So yeah, we're talking about energy of chemical reactions. In chapters 3 and 4, we looked at balancing, we looked at stoichiometry, and so we'll see how we can treat energy in terms of stoichiometry as well. So last week we talked about how we can measure or talk about energy of reactions or energies of samples. We can talk about kinetic energy and potential energy. So these terms are back and important again, where kinetic energy is related to your temperature of your sample and your potential energy is related to your position. I mentioned to you prior that you should write in your diary tonight before you go to bed, when talking about potential energy of samples, what we see is that potential energy is lowest or most negative when your particles are attracted and they're close together. So when we look at these two samples, we see, in sample A, the particles are close together, but in sample B, they're far apart. So that means sample A has the more negative potential energy, while sample B has the more positive or, higher potential energy here. For chemists, we want negative potential energies because that means that your particles are attracted to one another. And that kind of differs from physics, because I feel like in physics, typically potential energy was always maximized, but for chemists, we want the most negative potential energy. So to recap what we did last week, for these two samples, we were able to deduce that sample B had the greater kinetic energy because of its temperature. Also, sample B had the greater potential energy because the particles were further apart, more positive potential energy. So therefore, sample B had the greater internal energy. So thinking about trying to turn a solid sample into a gaseous sample, we actually have to increase the total internal energy of those substances. So we see that here. For chemists, we don't really care so much about the absolute internal energy of our samples at certain points in time. What we care about is how energy changes during a process. So what we care about, what chemists care about, is how much energy does it take to go from state A to state B. We can measure this fairly easily, but what we can't measure are the individual energies of the final and initial conditions. Like, I don't know what the absolute internal energy of this solid sample is. I don't know what the absolute internal energy of this gaseous sample is, but what I can measure is the difference of that whole process. And that's what we care about. What we're going to look at for the rest of this chapter is change in internal energy or change in energy of the systems, not so much absolute energies. Yes, we can kind of look at it from like a conceptual way, but never are we actually going to calculate it. All right. So let's talk about how we can measure changes in internal energy for a chemical process or even a physical process. So how can we measure it? So we already introduced this first equation that the change in internal energy for a process is just the final condition minus the initial condition. But we have a problem. We can't, like I said, we can't actually measure these two values. So what chemists use instead is we can say that the change in internal energy for a process is equal to the Q, or the heat involved with that process, or plus the work involved in that process. All right, so we're actually going to most likely use this version of change in internal energy, relating it to the work and heat involved with that chemical process. So we have to define what work and heat are. So like I said, Q, that's the first portion of this equation. This is something we can measure in lab. We call this heat. We're going to measure it by temperature change. So what I mean by temperature change, this is something we can absolutely measure. Where change in temperature of your sample, when we talk about changes of things, that delta sign, it's always final minus initial by convention. Final minus initial, okay? So you take your initial temperature of your sample, your final, and then you subtract final from initial. So if the temperature increases of your sample, delta T will be a positive sign, but if it decreases, it's a negative sign. So based upon those signs of Q that we can calculate in a little bit, I'll show some equations a little bit later. We can also define endothermic and exothermic reactions. We talked about this a little bit before, where again, signs are important. It tells us the direction where energy is going, either into the system or out away from the system. So what we see here is that when heat of your system is positive, what that means is your system is absorbing heat. It's absorbing Q, so to say. So Q is positive in this case. We call this an endothermic process, endothermic, all right? Versus when your reaction releases a bunch of heat, oftentimes in a fiery fireball, that is an exothermic reaction. But Q is negative in this case because your reaction is losing that heat. So in a fiery explosion, the reaction is losing heat, and us, we are the what? We are the surroundings. We are gaining that heat and enjoying the fiery explosion, all right? So that's a negative sign. Your reaction is releasing that heat, right? So that's heat. Exo and endothermic, those are the terms we use to denote sign and direction where energy is going. So let's talk about work. So work for a chemical process or even a physical process is, I defined the equation that chemists use to define work, where work of your system is equal to negative external pressure, this is just going to be a constant, times the change in volume of your gas sample. So chemical reactions can do work when things like gases expand or contract. So that is what as chemists we're going to define as work. Volume expansion or compression with gases, all right? So this is called a pressure volume work, where things are expanding and contracting. So we also have to be careful about signs here. We can have a positive work and a negative work in relation to our system. So this is how it goes, all right? When work is done on your system, I like to think of it this way, okay? I can take a balloon. Let's say a balloon is my reaction. That's my system. If I squeeze on that balloon, the volume gets smaller, right? So if I'm squeezing on the balloon, squeezing on the reaction, I'm putting work into the reaction. I am the surroundings, right? I'm the surroundings. If I squeeze on that balloon, I'm putting work into that reaction, into the system. So the system is what? Gaining or losing work? Gaining work in that case, since I am the surroundings, I'm squeezing on that reaction. So here what we see is that work for your system is positive when it undergoes compression. And the reason is because the surroundings is doing work on the reaction, so the reaction is gaining that energy, right? Or you can just plug it right into that equation. If I squeeze on this balloon, on this reaction, how is the volume changing? If I squeeze on it, it gets smaller, right? So what is the sign of delta V if it gets smaller? Negative. So plug in a negative sign into this equation. A negative times a constant times a negative is what sign? Positive. So it works that way too. If you don't know, just understand how delta V is related to your sign of work. The next one here, when work of your system is negative, I don't know, it's sometimes hard to just get our heads around, But again, if you just understand how delta V is related in this work expression, you'll still get the correct sign. All right, so when work is negative, what that means is your reaction or your system is doing work on the surroundings. That's what it means. So it's a little bit different here, where I like to think, okay, if I'm the balloon, I'm the reaction, and I'm pushing out against the surroundings, I'm doing work against the surroundings. I'm putting work into the surroundings. So what we see is a volume increase that we see, not compression, but expansion. So what we see here is that system does work on surroundings. It's pushing out against your surroundings. What you'll see is a volume increase. So delta V is positive in this case. And so if we put this positive delta V back into this work equation, what sign of work do we get out? Negative, all right? So the equation works, the concept works, definitions here work. I'm a fan of the equation, so I get the sign right. Because as long as I know what is the sign of delta V, then I can figure out what is the sign of your work of your system, as long as you know how your system is changing volume. All right, so let's put that, not quite, almost all together. All right, so we've talked a lot about system and surrounding, so I need to define those things a little bit better here. I want to remind you that as chemists, what we care about is the chemical reaction. So I oftentimes use these terms interchangeably, like I say Q of the reaction, or I say Q of the system. Those usually mean the same thing, right? That's usually what we care about. We care about how is the reaction losing or gaining heat? How is the system gaining or doing work, right? So what we care about is the chemical reaction or the systems. So when we define what our universe is, we have our reaction, our thing of interest, but then we have everything else in the universe. So we define that as the surroundings. It's the rest of the universe except the system that's understudied. And so that's how we encompass the entire universe. We have our system, the thing we care about, and everything else. That is the surroundings, all right? So we can make this definition, yeah, the universe is equal to your system, the thing you care about, and the surroundings. So where do we fall in? Where do our observations, where do we fall in this? We are the what? Surroundings. We are the surroundings. The chemical reaction is the system. So we got system, we got surrounding, that those two things put together, that is our universe. So if we put this together with the first law of thermodynamics that says energy cannot be created nor destroyed, what we can say is that energy that is generated in our chemical reaction, in our system, has to be transferred to our surroundings. Again, because the first law of thermodynamics says the energy of the universe always stays constant. So if the reaction generates energy, that energy had to come from somewhere. It comes from the surroundings. So what we can say here is that the negative energy change of the system is equal to the positive energy change of the surroundings. Or you can think of it this way. The negative of whatever was lost is equal to the positive of whatever is gained, right? We're going to be using this a lot. Do not forget this negative sign, right? The negative of something lost is always the positive of something that's gained, right? So what we have here, again, we are the surroundings, okay? So typically what's going to happen is we can measure this. We can measure the energy changes of the surroundings, and we're going to relate that back to the system, all right, or the reaction. That's kind of a precursor to calorimetry, what we're going to do here in a little bit, and what you'll do in the IHT lab. I don't think that happens until after fall break, I think. I'm not sure. It does? Okay, perfect. Okay, perfect. It's one of the most math-intensive things that you'll do in this course. But just take my hand, follow me into the dark, and do everything I tell you to do. Okay, so let's put it all together with these signs, because I told you if you mess up in this chapter, what are you going to mess up? A sign. All right, so let's look at this. Okay, so let's be careful with signs. Recall, we have a way to measure change in internal energy. We can do final minus initial of energy, but let's not. Let's relate it to the heat and work done by our system. So let's do a little bit of reading comprehension here. let's say we conduct a chemical reaction that absorbs 25 kilojoules of heat and does 10 kilojoules of work on the surroundings. What is delta E of the system? So what a lot of students will do is see, oh, delta E equals Q plus W. So the answer is 25 plus 10. But not necessarily. Okay, we got to do reading comprehension. We need to make sure the signs are right. I'm just telling you, the energy involved here, but what I don't tell you is the sign. So we have to infer by the language that's used here, what is the sign of each of these values. So let's break this down. So if the chemical reaction absorbs 25 kilojoules of heat, it's describing Q, specifically Q of the reaction. What is the sign of this Q? If the reaction is absorbing 25 kilojoules of heat, is it positive 25 or is it negative 25? Positive, yes, because it is absorbing. So we got to read it, because if I would have said, oh, this reaction releases 25 kilojoules of energy, would it be positive 25? Nope, that would be negative 25. All right. Okay, and then the next one is, does 10 kilojoules of work. So obviously we're talking about work of your system, but what is the sign? Is it positive 10? It is actually negative 10, because the reaction is doing the work. I like to think the work is leaving the reaction. That's how I like to think of it. So if the work is leaving the reaction instead of being gained by the reaction, it is a negative sign. So this is negative 10 kilojoules. And so now when we put these values into our delta E equation, we understand that it is 25 kilojoules plus negative 10 kilojoules. So our answer is 15 kilojoules, all right? We can't just take the numbers, plug them into the equation. We have to infer what those signs are based upon the language that's used here, right? Okay. Okay, so let's do one more where we are utilizing, our understanding of signs, delta E, and how Q and work are related. Okay, so we have a exothermic combustion reaction occurring in a piston in our car. In which scenario is delta E of our system always negative? Is it when the piston moves up or when it moves down? Right, there's a lot of moving parts in this question, so let's kind of break it down. This question is asking, when is delta E of your system negative? All right, so that means we're not actually calculating anything, we're just trying to determine the signs of things. So given what's in this question, do I already know one of these variables? Do I know Q or do I know W already, given what's in the question? Let's read the whole question. I tell you, this is happening in your car engine. It's an exothermic combustion reaction. Notice I have it bolded. That information tells us what variable? Q, yes, Q. So if it's an exothermic combustion reaction, what is the sign of Q? Negative, yes, it's exothermic. So if the goal here is I want to know when is delta E negative, I already know Q is negative. What kind of work am I looking for? So a negative number plus what kind of number will always give a negative number? A negative number, all right? So our goal is we want to know when is work of our system negative. That is our goal, okay? Because when work of the system is negative, if I add a negative number to a negative Q, I will always get a negative delta E, right? So we got to figure out in which one of these scenarios, when the piston moves down or up, is work negative. So let's think about this. We have like a gas cylinder. When the piston moves down, how is the volume changing? Decreasing. When the piston moves up, how am I changing the gas? It's increasing, all right? So I can't off the top of my head figure out what is the sign of work, so I will just write the equation that helps us determine the sign of work, which is work of our system equals negative pressure, which is a constant delta V. So if I'm looking for a negative work, what kind of delta V am I looking for? A positive one? Yes, a positive one? Okay, good. All right, yes, so I can do math. So what we're looking for here is a positive change of volume. Okay, so when our reaction increases its volume, it's doing work onto the surroundings, so work is negative. And so then when we have a negative work, a negative Q, we will always get a negative delta E. So which one of these is our actual answer? When the piston moves down or when it moves up? When it moves up, because this one is related to a positive delta V, right? So that's like a little bit of backwards thinking about signs and really understanding not just, can you calculate things, but understanding the significance of the signs of Q, work, and its relationship to total change in internal energy. So these are both examples that really require absolutely no math. Basically, it's really about the signs and understanding that concept. Okay. So in both of these examples, we calculated change in total internal energy, all right? So, okay, so this is change in internal energy. Often you'll see, on Wikipedia or when you Google energy processes, it'll tell you that change in internal energy is a state function. And we're gonna utilize this property in a little bit. What that means, that internal energy change is a state function, is it means it doesn't matter the path we take during a chemical process or during a physical process. All that matters is the total change of where we started and where we ended. So it doesn't matter if we take 8 different steps to get from beginning to end, or if we take 1 step to get to beginning to end. Those energy changes for those 2 processes will be the exact same, as long as where we start and where we finish are the exact same. So that's what it means by a state function. All that matters is where we begin and where we end. So here's an example. Here's 3 different samples: a solid, liquid, a gas. On the street, when we turn a solid into a liquid, what do we call that? Solid to liquid? Melting. Yes, melting. Liquid to gas? Boiling, yes. So if we see here, there's an energy change from solid to liquid, and then there's an energy change from liquid to gas. What we see here, the magnitude of these arrows, they're a little bit different, all right? It takes a little bit more energy to turn a liquid to a gas than it does to take a solid to a liquid. So those are 2 different processes. But what we can say about delta E being a state function is it doesn't matter the path we take to go from beginning to end. So what we can say is that the energy to go from solid to liquid, or sorry, solid to gas, like if we wanted to go from this energy place to the gas one, is the same energy it takes to go from solid to liquid to gas. So basically, we can do this physical change in 1 step, or we can do it in 2 steps. Those 2 energy changes are equivalent. I have that mathematically up here. So what I'm saying is that green arrow, the energy to go from solid to gas, is actually the same energy it takes to go from solid to liquid plus liquid to gas, right? So we can add up these steps to equal 1 entire process, and we're gonna utilize this property in a little bit when we talk about Hess's law. All right. So this is an example about changes in internal energy, E. That's what we've been talking about all this time. This will be the last time I talk about delta E, change in internal energy. And it's because it's hard to measure on Earth, okay? Or like on benchtop, benchtop chemistry in lab. Change in internal energy is both the heat and the work of a chemical reaction. But for the most part, when we do chemical reactions in lab, gases typically aren't produced. So we can actually, for the most part, ignore the work component in chemical reactions, and all we're going to really focus on is the heat component, all right? So when we do labs and experiments in lab, we are working under the assumption that pressure is constant. So what we're gonna say is that all of the heat generated under these conditions corresponds to the change in enthalpy of this reaction. So basically, instead of thinking about delta E, we're gonna think about delta H for chemical reactions instead, where heat, and that's something that we can easily measure in lab, is related to delta H. It's still energy. It just kind of ignores that work term, all right? So we're going to kind of just ignore that work term from here on out and just focus on the heat term. Specifically, we call this enthalpy delta H. Enthalpy, so delta H is also a state function that just like change in total internal energy. And the terms endothermic and exothermic are still used here. So whether or not delta E or delta H is positive, that's endothermic, or delta E or delta H is negative, that's still exothermic. All right, so we're gonna just switch out the E with an H now and just talk about heat. Calculations will be a little bit easier here. So basically, yeah, in summary, when we're under constant pressure, like benchtop conditions, the heat generated by the reaction is described by delta H, and that's what we're going to talk about now. Okay, all right, so we're going to talk about delta H now. So no more E's, no more work. Okay, so let's talk about enthalpies of reactions and how we can talk about energy in reactions in relation to our balanced chemical reactions that we introduced in chapters 3 and 4. All right, so what we see here, enthalpy is a state function, meaning it just matters where we start and where we end. But we also see that enthalpy is an extensive property. What does extensive mean? It means it matters how much matter we have, okay? Like an example of an extensive property, mass, volume. The mass and volume of a sample that you measure depends on the size of your sample. But if we were talking about like density, density is an intensive property. It just matters what is the identity of that sample. So what we see here is enthalpy is extensive. So here I have a reaction. Hydrogen plus oxygen gives us water. And I tell you that this reaction, as written, generates negative 484 kilojoules of energy. Negative meaning that the reaction releases energy in a fiery fireball, okay? So that means if we manipulate the reaction, if we don't react to moles of hydrogen and instead we react only 1 mole of hydrogen, what happens is we change the amount of delta H associated with that reaction. So I like to think of it this way. How is this first reaction different from this second reaction? So here's the first reaction in pink. Here's the second reaction in pink. How did I manipulate that reaction? What did I do? I cut it in half, right? Instead of reacting 2 moles of hydrogen, I'm only reacting 1 mole of hydrogen, half a mole of oxygen, and I'm only making 1 mole of water. So do you see how I said that this reaction was cut in half? Do you see it? Yes, all right. So if I cut this reaction in half, see all the mole amounts, all those coefficients change by a half, we also have to adjust delta H. So what we see here for this second reaction is I divide that delta H in half. So when I react only 1 mole of hydrogen, I only generate 200, can I do the math, 242 kilojoules of energy, all right? So the idea is like, you know, if a full gas tank can take you 400 miles, how much will half a gas tank take you? 200 miles, all right? So what we see is energy scales with how much matter that you have present, right? So that means if I doubled this reaction, then I'd have to double delta H. If I tripled this reaction, I'd have to triple the amount of delta H, the amount of heat that's generated. So we can, you know, manipulate the coefficients of a reaction, but we can also reverse a reaction, all right? So notice here, we're taking hydrogen plus oxygen to give water. That's the hydrogen balloon demo that I've done a million times. Or we can reverse the reaction. So instead of taking hydrogen plus oxygen give us water, what if I take water and split it into hydrogen and oxygen? This is actually called water splitting. Okay, water splitting. All right, so when we reverse a reaction, how delta H changes is not numerically, but the sign. All right, so if we reverse a reaction, what we're gonna do is just multiply the delta H by a -1 to reverse that sign. So what we see here is that this water splitting reaction actually requires 484 kilojoules of energy. So this one we flipped, this reaction we flipped, so we flipped that sign of delta H, all right? So what we see is When we make water, when we do the hydrogen balloon demo and we make water, H2O is a product, we release energy. But if we take water and split it back into hydrogen and oxygen, that requires energy. We literally have to plug this reaction into a socket, into an electrical socket, to make the reaction run, right? Versus when we do the hydrogen balloon demo, that energy is just released spontaneously. With that negative delta H, but splitting water is positive. All right, so yeah, we will utilize these ideas in a little bit with Hess's law. Okay, so because delta H is an extensive property, we can write delta H in our balanced chemical reaction. We can actually use delta H like stoichiometry, all right, in chapter 3s or chapter 4. As long as we write what's called a thermochemical equation. What a thermochemical equation is just a regular balanced chemical equation, but we have this delta H at the end. So what this means is when I react 1 mole of methane with 2 moles of oxygen, negative 890 kilojoules of energy is released. That's what this means. This is a full thermochemical equation where it's just a regular balanced chemical equation, but it has this delta H term in it as well. So what's great about a thermochemical equation is that it works the same as all stoichiometry we did in chapter 3, all right? Remember, what unit do we have to be on to get on our balanced equation to use the coefficients? What unit? Moles, okay? So once we're in moles, all right? Like if I know how many moles of methane I have, can't I go to moles of oxygen to figure out how much oxygen do I need? Or I can go to, how many moles of CO2 do I need? Or how many moles of CO2 do I produce? If I know how many moles of methane I have, I can also figure out how many moles of water I produce. So that was all chapter 3. So what a thermochemical equation allows us to do is, as long as we're in the unit of moles, I also know I can make the relationship to delta H. So if I write all of these equalities out, I can basically just use the stoichiometry that's already here and relate it to, relate it to the delta H value that's given. So if I write out the full equality here, I can say 1 mole of CH4 is equal to 2 moles of oxygen, which is equal to 1 mole of CO2, which is equal to 2 moles of H2O. If this was chapter 3, those are all the equalities we would use for stoichiometry. But what's different in chapter 5 is I can also say, this reaction of all those things releases 890 kilojoules of energy is released. It's released because it's a negative sign, all right? So we just added this new thing that we can use with stoichiometry. So let's do an example. How much energy of heat would be produced if we combusted 24 grams of methane in excess oxygen? So really, this is just a dimensional analysis question, stoichiometry question. We are given how much methane we have. If this was chapter 3, maybe I would have asked, how much CO2 do you produce, right? That's chapter 3. But instead of going to a product, we're just going to go to, how much delta H do we produce instead, right? So it's just the stoichiometry changes. All the other steps are the same. If I start with 24 grams of methane, I need to be in moles to use the balanced chemical equation. So I have to use the molar mass of methane. So that's 16. But where am I going to put the 16? On the top or the bottom? Bottom, good. Just want to make sure you guys still got it. All right. So we have this many moles of CH4. Now I'm in moles, so I can get on the bus to use the balanced chemical reaction. But remember, I don't want to go to any product or any reactant. I want to go to delta H instead. I want to get off the bus somewhere else. So what we're going to do is use this equality. 1 mole of CO2 equals negative 890 kilojoules of energy. So I'm going to put the 1 mole of CH4 on the bottom, negative 890 kilojoules up top. When we calculate this, our calculator says negative 1330 kilojoules. right? But remember that negative sign just implies the direction. Seeing a negative energy is kind of weird. So a just as correct answer would be saying 1,330 kilojoules of energy is released. Both of these answers are equivalent to one another, all right? Because just seeing negative energies are weird, all right? The negative sign just implies what direction energy is traveling. All right, let's do one more example. This time we're going to work backwards. So if I tell you that we do this reaction and it releases 2,400 kilojoules of heat, how much water is produced? Right? This is basically stoichiometry. We are given delta H. We want to go to water, right? Thankfully with energy, you know, we're already in energy. We don't have to go to moles, all right? But the equality that we're going to use here has to relate water with delta H. So that equality is 2 moles of water equals negative 890 kilojoules of energy. So I'm already telling you that this 2,400 kilojoules of energy is released. So you can think about, you know, there's like an implied negative sign there already. Don't let the negative sign like mess you up here. All we're going to be doing is multiplying by the stoichiometry to take us from delta H to water, where we want to go. So you can think of, okay, yes, 890 kilojoules on the bottom, 2 moles of water up top, right? But we want grams of water, so then let's take its molar mass. 1 mole of water is 18 grams. And so we get that, yes, when this reaction releases 2,400 joules of energy, remember that negative sign is implied because I say released. We can calculate, use the relationship between delta H and moles of water to then get to grams of water to see, okay, about 97 grams of water will have been produced in this reaction if that amount of energy is released. So notice if I didn't use that negative sign there, you'll notice if you left that negative sign with 890, then you'll get like a negative 970 or 97 grams. Again, don't let the negative signs mess you up. The sign just tells us the direction energy is going. So whether this stoichiometry step, you put 2 moles of water over positive 890 kilojoules. We just need the ratio. That negative sign, again, just tells us the direction. Since both of them say that energy is being released, we can just kind of take away that negative sign as to not have a negative sign propagate itself throughout this reaction. That's just a common mistake that students make. They just don't understand the significance of the negative sign. All it's telling us is the direction energy is going. You can't make a negative amount of water. All right, okay, so don't let the negative sign mess with you. Okay, so yes, delta H matters about how much material you have there. Delta H is a extensive property. So let's do a demo. We've done this demo before, but let's just do it again anyway, where we have 3 different reactions, but we're gonna look at this reaction, but from a different standpoint. All right, so when we did this reaction like last week, I just wanted us to, you know, figure out what's your limiting reactant, how much product do we make, all right? So we did this reaction before where, you know, I react 1 equivalence of acid with 1 equivalence of base to give us 1 equivalence of a gas. And I said, okay, with reaction A, I have a 4-to-1 ratio. So how much gas do I produce in this first reaction? +1. How about the second reaction? +2. And then the third? +4. You see how I got that? That's chapter 4, right? And it allowed us to kind of dabble with limiting reactants. But notice, I'm generating a gas. Do you remember when I did this demo, what happens to the balloon? They expand, right? So their volume changes. So if a gas is being generated here, so let's, if a gas is being generated, how is delta V changing in these processes? It's increasing. So how is work of our system changing for these different reactions? Is it going up or is it going down? Or is it negative or is it positive? It is negative because delta V is positive for all of these reactions. So that means work of our system is negative. So, but we just learned that energy, it's an extensive property. So if the first reaction generates 1 unit of gas, the first reaction is going to lose a negative, I guess, since we're not really using units, we're just using ratios, a -1 amount of work. So then therefore, the second reaction will lose what extent of work? -2, and then the last one, -4, all right? So we see this propagate itself in this chemical reaction by the extent of the volume changes of this reaction. So here's reaction A, where it's just a little bit, 1 equivalence of the base. Oh no, is there a hole? Go. Okay, so this one was a very small amount of work. Oh, there it goes. Okay, there we go. Small amount of work being done by the reaction, so it's a negative work. Here's the second one, doing a little bit more amount of work because its volume is increasing more than that first one because there's more reactants reacting. So we can see the balloon's a little bit bigger. And then the last one, the reaction is doing the most amount of work. Don't explode on me. The last one is doing the most amount of work because, again, its volume is changing the most, all right? Because there's the most amount of matter there. All right, so it's scary. Whoops, scary. All right. Yes, so we see that this limiting reactant question where we compared the extent of the amounts of gases that are made also relates to the amount of work. And so in all of these reactions, because the volume is expanding with the reaction, work of the system or the reaction is actually negative because delta V is positive, work is negative. Okay, so there's our demo. Cool. Okay, do a couple more, and then I will do another demo. Okay, so let's put this all together into a strategy. So I hope that, using delta H in a balanced chemical reaction, using it with stoichiometry really isn't anything new, okay? If I give you a balanced chemical reaction with delta H, you're just kind of like adding that skill in your toolbox that you already have. So let's look at a new way we can utilize that idea that enthalpy is an extensive property and it's a state function. And that is using Hess's law, all right? So Hess's law is a strategy to basically take multiple chemical reactions, combine them in a special way to get a new enthalpy of a different chemical reaction. It's like a puzzle, all right? So the strategy is I will typically ask you like the enthalpy of a target chemical reaction, but I'll give you the puzzle pieces to get there. And so what you're going to do is manipulate those given chemical reactions until you get your target chemical reaction. And you just have to think to yourself, okay, do I have to multiply by a coefficient? Do I have to flip a reaction? And keep in mind all those manipulations you do to get to your target chemical reaction. I think it's better to just do examples than to explain the strategy. But the idea here is your focus is this target chemical reaction and you're gonna manipulate what's given to get you there. But note, if you flip a reaction, you also have to flip the delta H of that given reaction. If you have to double or triple a reaction, you also have to do that to delta H. And so what we'll see here is we're combining multiple chemical reactions, hoping that some things cancel out. So if you have a reactant, so if you add up your chemical reactions and you have a reactant show up on both sides of the chemical equation, they cancel out, right? Or if it looks something like this, let's say you have 2 X's on your reactant side, 1 X on your product side, do all of the X's cancel out? Nope, just one of them. So what your new reaction will look like is this. X plus Y gives you Z. And then this first one would just B plus B goes to C, right? So we need to understand that we will manipulate given chemical reactions and cancel things out of our chemical reaction. If things are on opposite sides, they cancel out. So let's just do an example. I think it's easier just to do an example, all right? So I have 2 reactions that I give you, and I give you the delta H's for them. And I'm asking you, what is the enthalpy change of this reaction? So I like to think, oh, this is my target reaction, your target reaction. right? I want the delta H of that. So this is my strategy. Take one substance at a time and try to match the given reaction to the target reaction. So let's just look for this first substance. Let's try to get this AB2 in the right place and in the right quantity, right? So let's focus on that first substance. So I ask myself, which reaction has AB2 in it? The first one or the second one? The first one, great. Then I ask, is that substance on the correct side? Nope, it's not, all right? I need AB2 on the reactant side. Right now it's on the product side. So what do I have to do to the reaction? I have to flip it, all right? So what I'm gonna do is flip reaction 1. But is that everything I have to do? I have to flip the reaction to get the substance on the right side, but is that substance in the correct number? It is not. I have to do what? Double it. So I'm gonna flip this reaction and double it. I'm gonna do both of those steps. And I'm not gonna skip this step. I'm going to literally rewrite this first reaction flipped and doubled because I just wanna make sure that things cancel out the way I want it to, all right? So let's rewrite this reaction flipped and doubled. So the products become the reactants now. So 2AB2 goes to what? 2 A's and 4 B's. So I flipped and doubled the reaction. So what does that mean about delta H? I have to flip and double it, right? So that number that's given, so negative 35, I have to multiply it by 2 and by negative 1 because I flipped and I doubled it. All right. So I got the AB2 on the correct side, right? So that means I just have reaction 2 to play around with. So here's my strategy. You might just go down the list and go, okay, let's put AB2 in the correct place. Now let's try to put B in the correct place. But let's look at this. B, which reaction does B show up in? 1 and 2. So that's a problem. So this is my hint for you. If a substance shows up in 2 places, just skip it. Just skip it and move on to the next thing. And we're gonna just pray that the B's end up being what we want at the end by canceling out. So I'm gonna just skip B because it shows up in 2 reactions. And I'm gonna focus on the last substance, A2B5. Because A2B5 just shows up in reaction 2, and that guarantees me I can ensure that A2B5 is in the right number and in the right quantity, right? So let's look at A2B5, it's right there. Ask yourself, is it on the right side? Yes. Is it in the right quantity? Yes. So we're just gonna add this reaction as is. So we're just gonna literally rewrite it, okay? Rewrite it as is. So 2A plus 5B gives us A2B5. What do I do to delta H? Nothing. So it's just negative 90 again, all right? This is the reason I write the new reactions because I want to ensure I get my target reaction at the end. So let's add these 2 reactions up, okay? So add up all of the reactants on the reactant side and all of the substances on the product side. Try to cancel things out before you get your total added reaction at the end. So we see after we add these 2 reactions up, we get 2 ABs. That's exactly what we wanted, okay? But do the 2A show up at the end? They do not, because look, there's 2A here and 2A on the product side. So see how those cancel? All right, so I don't have to rewrite those 2A's at the end. What else cancels? The B's, but do all of them cancel? No, they don't. Only 4 of them cancel. So those 4 cancel, and then how much are left over here? Just 1, all right? Just 1 of those B's. And is that what we wanted? Do we want 1 B left over? Yes, we did. So that's good. We skipped B. Skip B because it shows up in 2 different reactions and just pray that it ends up being the right number that you want at the end, and it did. All right, so there's 1 B left over and then the A2B5 at the end. And so we can confirm that adding those 2 reactions give us our target reaction. And so the delta H for this reaction are those delta H's that we inventoried a little bit before. Remember, do make sure that you do the manipulations to delta H of whatever you did to the reaction. So I think mathematically this is positive 70 minus 90. So delta H is negative 20 kilojoules for this reaction. So it's just like a fun little puzzle, all right? So let's do one more. Let's do another one. Again, I just go through, I look at the target reaction, I go through each substance and make sure I pick a reaction that puts that substance on the correct side and in the right number. So let's do the first one. Let's make sure carbon is in the right place. So what reaction am I going to work with? Reaction 2. How am I going to manipulate reaction 2 to ensure our target? We're going to do what? Times 2. Do we need to flip it? No. So we're just going to multiply that second reaction by 2. So I'm going to put a times 2 by delta H to remind myself I doubled it. And I'm going to rewrite it with that doubling because I want to make sure that the things cancel at the end how I want to. So 2 carbons, and I'm just going to drop the states here. The states don't really matter unless like we had carbons of different states. So I'm just going to make it a little bit prettier here. So 2 carbons plus 2 oxygens gives us 2 CO2s. All right, and so that delta H is going to be negative 394 times 2. All right, so that's the carbon. Next, let's move on to hydrogen, right? What reaction do we want to work with? Reaction 3. So if you look here, there's hydrogen, and hydrogen just shows up in reaction 3. It doesn't show up anywhere else, right? Correct. So just reaction 3. So is hydrogen in the right place? Yes. Is it in the right number? Yes. So we just rewrite reaction 3 as is. I'll even write as is to remind myself, oh, I don't have to do anything to delta H. So just times 1, I guess. So I'm just going to rewrite it. A hydrogen plus half an oxygen gives us a water. All right, so that delta H is as is, so negative 286. And then the last thing here is, let's pick a different highlighter, C2H5. And so we see that shows up in reaction 1. Is C2H2. Is C2H2 on the right side? No, so flip it. Is it in the right number? Yeah, so we're just going to flip it. So this is a times negative 1. I'm going to write this reaction flipped. So this is reaction 1 flipped. So we have 2 CO2s, a water, a C2H2, and 5 halves O2. And so the reason I write all these reactions out is because I want to make sure that these 3, that I manipulated all 3 reactions correctly to give my target reaction. So that means canceling things that I need to. All right, so there's a lot of stuff going on. What cancels? Tell me one thing that cancels. The H2s, okay, H2O, sorry, H2O, oh no, where's H2O? Yep, H2O cancels. What else cancels? CO2, CO2, CO2. What else cancels? Yeah, let's dissect this one a little bit more, because see how like O2 shows up in a lot of places, and I actually don't want O2 in my target reaction. So something really special happens here. So 5 halves O2 is the same as what, 2.5? And then how many O2s are right here? 2.5, yay, right? So all of the O2s, do they cancel? Yes, they do, yes. So we just gotta be careful with those fractions. So all of those cancel. So what is left over? We have 2 carbons plus a hydrogen gives us a C2H2. Is that what I want in that target reaction? Yes, it is. So I can confirm, yes, doing all that manipulation to those 3 reactions gives us our target reaction. I forgot to write that last reaction flipped. So where do what delta H do I put right here? What number do I put right here? Negative 1300? Positive 1300, very good. So positive 1300, and so I will just add up all of those numbers with those manipulations I did, and get that delta H that's in the corner written there. You can do that math. It's positive 226 kilojoules for that reaction. So as written, 2 carbons plus a hydrogen molecule is actually, to give acetylene, is actually an endothermic process. All right? I like Hess's law. It's like a little puzzle. This example had 3 given reactions to get a target reaction. This first one was a little easier. It was 2 given reactions to get a target reaction. If you look at my overview sheets with all of those worked out keys, I think I have one example with like 6 different given reactions. So you can practice kind of those more complex ones on your own. But I'll say for the most part, 2, 3, or 4 given reactions is basically the max that we would ever give you. All right. So that's how we can use enthalpy. We can use it with stoichiometry, and we can use it using Hess's law. All right. So now we have like 25 minutes. We're going to move on to the hardest section of the chapter. Lots of math. And that is calorimetry. Okay? So keep this in your back pocket for your IHT lab. You're going to do exactly this in your IHT lab after fall break, right? And I mentioned, if you're going to screw up in this chapter, it's because you messed up a sign, and it's going to happen in this section. Here's the thing. I want you to make the mistake. Make the mistake loudly and boldly so I can correct you. All right, we're going to make the mistake a lot with that negative sign. All right, so what is calorimetry? I mentioned before, we're going to calculate enthalpy 4 different ways in this chapter. Hess's law was one of them. And then I think the second one here is calorimetry. So this is a way we can actually measure and determine enthalpy of a reaction. And we do this in lab experimentally. But in order to measure enthalpy and energy changes of in a process, we need to come up with a couple more equations here to do these measurements. So we got to define some terms here: heat capacity and specific heat. These are different properties, but I know for a fact you will mess up these definitions, but they are in fact different. All right, the first one, heat capacity, is something that we can measure for an object. It's the amount of heat required to raise an object's temperature by 1 Kelvin, or 1 degree Celsius, okay, or 1 degree Celsius. So heat capacity, it depends on the size of your object. So this is an extensive property, okay? Think about it. Think about how much energy it takes to heat up a cup of water versus a pot of water, all right? Those 2 objects have different heat capacities because they're different sizes. It only takes, some energy to heat up a cup of water, but a pot of water is going to take a lot more energy, all right? So the unit and equation we use to think about heat capacity, how much it takes to heat an object, Q, this is the same heat we talked about before, is equal to heat capacity times the change in temperature for that object. So just based upon the units that are here, Q is in the unit of joules, delta T is in the unit of usually degrees Celsius or Kelvin. And so that means heat capacity has to be in the unit joule degree Kelvin. So those are how our units work out, all right? So we can rearrange this equation to say, oh, heat capacity is equal to the Q of your process over the change in temperature of your process. So that means the unit of this guy of heat capacity can be joule degree Celsius, like I said before, or joule Kelvin. It's the same value. And I'll show you why in a second. Right? So that's heat capacity. It's heating an object. It's an extensive property because your object could be big or it could be small. On the other hand, we can talk about specific heat. This is very important if we're ever working with pure substances, like heating up water. Water is a pure substance. Or heating up a bar of copper. Copper is a pure substance. You can look up the specific heats for elements, for substances, for compounds, and they have specific heats, the amount of energy to change the temperature of those substances. So what we see, the definition of specific heat is the amount of energy in joules to raise a gram of an object's temperature by 1 Kelvin or 1 degree Celsius. Again, it doesn't matter. So what we see here is the equation for a specific heat is a little bit different. It's still Q, but now we have to multiply by mass of your sample times specific heat times delta T. I always say that the Q for specific heat is Q equals MCAT. MCAT. So if you just ignore the S, you know, like that exam that a lot of you will have to take. So Q equals MCAT. And so what we see when we kind of rearrange this is we can say, oh, specific heat is Q over mass over delta T. And so that also gives us the unit of specific heat. So specific heat unit can be joule gram degree Celsius, again, or joule gram Kelvin. Right? So those are those units that we're going to play around with. And so you might notice that there's a lot of delta T's here. Okay, there's a delta T here, delta T here. Whenever we talk about deltas, it's always final minus initial. All right. But you might be wondering, you know, why can I use degree Celsius and Kelvin interchangeably? And the reason is because all of these equations use delta T. Delta T. So the change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. But that does not mean that a Fahrenheit or a Celsius temperature is the same as a Kelvin temperature. So that's what I have right here, all right? That the change in temperature in Celsius is the change in temperature in Kelvin. It's the same number, but your Celsius temperature is not the same as your Kelvin temperature. Let me give you an example, all right? I have that right here, all right? Here's an example. Because this trips up a lot of people, right? So if I tell you your initial temperature is 0 degrees Celsius, your final temperature is 10 degrees Celsius, what is delta T here? Final minus initial. 10. It is 10. Do we all agree it's 10? Yes, it's 10 degrees Celsius. Okay, so let's convert both of these Celsius temperatures into Kelvin. All right, so what is our initial temperature but in Kelvin? Do you remember our relationship? Your Kelvin temperature is your Celsius temperature plus 273.15, but who cares about the decimal places? Let's just use round numbers right now. So what is our initial temperature in Kelvin right now? 273, okay. So then what is our final temperature in Kelvin? 283, yes, 283 Kelvin. So tell me, what is the delta T in Kelvin? 10, yes, 10, but 10 Kelvin. So see what I mean? That a change in temperature in Celsius is the same as your change in temperature in Kelvin. But look, the actual temperatures, so the difference between these numbers are the same, but the absolute numbers, the Kelvin and Celsius temperatures are different, all right? So in this section, since we're only talking about changes in temperature, we don't have to distinguish between, we don't have to convert all our Celsiuses to Kelvins. Oftentimes you'll see me write Kelvin a lot, and the reason is because on a computer, I don't like finding where the degree sign is. It's literally out of pure laziness. I'll write Kelvin a lot instead of the Celsius sign. So that's a small note. You'll see it as we practice this. Okay, so in this table, we have a bunch of specific heats of stuff, all right? So we can be really good at putting numbers in an equation, okay? But what did we learn about our the last two exams we've taken? Are they all math-based? No, it's pretty much 50-50 math concepts. Some people might fight me on that and be like, no, there's way more concepts. No, there's way more math, but it's about 50-50 concepts in math, all right? So we can't just be really good at plugging in the numbers into those equations. We also have to be good at understanding what those numbers mean. And so that's understanding these specific heats. Yes, they're numbers, but what do these numbers mean, all right? So here we see a bunch of samples. Water has this specific heat, 4.18. You're going to use this a lot in lab. We always give you specific heats if it's needed in a problem, all right? But I promise you, you'll probably remember what water is. It's 4.18, 4.184 if you want more sig figs there. And so there's your specific heat. That's how much energy it takes to raise water. 1 gram of water, 1 degree Celsius. It's actually a lot of energy because what we see here is that water has the highest specific heat of any of these substances. Methane, CO2, a lot smaller specific heats. These solid metals, 0.9 or 0.45, those are like aluminum and iron, have a lot smaller specific heats. So the significance of this, what we're looking for when we kind of gauge these numbers, is a large value of specific heat. So something like water. Water's is 4.184, means that more heat is required to increase the temperature of your sample. What it also means is that the temperature of your substance is not easily changed. That's what a large specific heat means. So like, you know, the, what's that thing called? The lake effect, right? So usually towns by large bodies of water typically resist, you know, crazy weather changes. Like that's a thing, right? The lake effect. And it's because that town is by a large body of water that can absorb a lot of heat, a lot of Q, a lot of joules of energy without changing its temperature. And that's the idea of the lake effect. And that's what a large specific heat means. I promise you actually understand the relevance and these magnitudes of specific heats. Pretend it's a really hot day and we're all going hiking and we finally get to like a break where we can take a rest, and you have the option. It's a hot day, it's really sunny. You have the option to sit on a wooden bench or a metal bench. Which one do you sit on? Wooden. Why does everyone say wooden? It's probably not as hot. Yeah, it's probably not as hot. So that means the wood bench is resisting temperature change, right? On a really hot day. Both of those seats are in the same sun, absorbing the same amount of energy, but all of us know to sit on the wooden bench on a hot day. All right, so why is that? It's because the wooden bench is resisting temperature change. So what does that mean about the specific heats of those two objects? Compare the specific heats of the wooden bench to the metal bench. What do we think? Which one's larger? Which one has the larger specific heat? Wood or metal? Wood, yeah. So what we see here is that the wooden bench has a large specific heat and the metal has a small specific heat. It changes its temperature a lot, and if we sit down on it, we're going to burn our butts. Right? Just to prove it to you, what those specific heats are, I think a wood has a specific heat of something like 2 point something. I wrote it down. What is it? 2.5 joule gram degree Celsius, and then metal is about like 0.9 joule gram degree Celsius. So yes, we see that wood does in fact have a larger specific heat. All right. Okay, a couple more. All right. So let's just do a couple calculations with our new Q equations, but we need to be careful that we use the correct one because I showed you two of them. One of them has specific heat, one of them has heat capacity. So based upon this question, which one are we going to use? So how much energy in kilojoules is required to heat up water by 75 degrees? The specific heat of water is 4.184. So which equation are we going to use? Q equals MCAT or Q equals CAT? MCAT, yes, we're going to use MCAT. Why? Because we have a gram amount of water and we have the specific heat of water. We're not going to use heat capacity. So really it's just plug and chug here. There's the mass, 75 degrees. Since it's raising that much, this is literally delta T, right? I'm just telling you, you're changing the temperature by that much, and there is specific heat. So we're just gonna plug and chug here. Mass is 150 grams. Specific heat, 4.184 joule gram degree Celsius. Delta T, 75. All right, and so what we see here, units canceled, grams, Celsius. So we are left with something like 47070 joules, but we want this in kilojoules, so move that decimal place 3 times. So this is about 47 kilojoules of energy to heat up that amount of water, right? That's a lot of energy. 150 grams of water isn't that much. It's 150 milliliters. That's like a small cup's worth, right? Okay, one more. Okay, so if we deliver 250 kilojoules of energy to a 6-pound cast iron pan that has a total heat capacity of 1.2 kilojoules per degree Celsius, how many degrees does the temperature of the pan increase? So notice the units that I give you. Which equation are we going to use? Q equals MCAT or Q equals CAT? Be careful. You might see, oh, look, there's a mass given, so we're going to use MCAT, but not necessarily. Did I give you any specific heat for this for the substance? No, I didn't. I gave you a heat capacity. Notice the unit of heat capacity, kilojoule per degree Celsius. Is there a mass unit in there? There's not. So we're actually not even going to use that 6 pounds. I gave you the total heat capacity of this entire object, so we are actually going to use Q equals CAT, right? Plug in everything. So Q is 250 kilojoules equals heat capacity, so 1.2 kilojoule degrees Celsius. So notice how both of these are in kilojoules, so I don't have to convert anything. And then delta T, that is what we're solving for right here, right? So solve for delta T, and you get that this pan should increase by 208 degrees Celsius. All we're calculating is the increase. I don't know what the pan started at, but if I did, then I could calculate the final temperature. I'm just calculating how much the temperature changed. All right. Okay, so we got 9 minutes. Perfect. Okay, so let's put it all together. Put it all together. Those ideas of heat capacity, specific heat. So let's compare without doing any calculations. I have a cup of water and a pool of water. Which object has a larger heat capacity? Or let me reword it. Really what I'm asking here, since it's heat capacity, is which object requires more heat to heat 1 degree Celsius? It's going to be the pool, because there's tons of water there, tons of mass, all right? There's tons of water to heat up there. And so I can say this because this question is specifically asking for heat capacity. But if we think about it differently, if I say what has the larger specific heat, what would you say? Yeah, neither of them, or they're both basically the same. They're both the same. Because remember, here, specific heat relates to the identity of the substance. Both of them contain water. For both of them, the water has a specific heat of 4.184 joule per gram degree Celsius. So they're both the same. So here's how we make the relationship. All right. Heat capacity is equal to our specific heat of our substance, specific heat times the mass of your object. So, if I have a gram of water, I can calculate the heat capacity of that gram of water. If I have 100 grams of water, I can take that 100 grams multiplied by specific heat to get the heat capacity of 100 grams. So the idea here is I can turn a specific heat to a heat capacity by multiplying by the mass of how much of your object is there, all right? So yeah, what we see here is heat capacity is an extensive property because it is specific heat times mass, the mass of your object, but specific heat is intensive. It depends on what object is there, or what the identity of your object is, all right? Okay, we've got 7 minutes, got one more demo to do. So these are the mathematical skills we need to move on to the next section of the chapter, and that is calorimetry. And so here we're actually going to calculate delta H of our reactions, but we need to be really careful, okay, about the sign of delta H. So we're gonna practice a little bit. We're gonna practice a little bit here in a second. But before I do that, the ways we're gonna use calorimetry, we're gonna do it 2 different ways. We're gonna do coffee cup calorimetry. You're gonna do this in lab as well. So we'll do the calculations in lecture and you'll do it in lab. And then we'll also do bomb calorimetry, but we'll just do this in lecture. You won't actually do it in lab, all right? So the idea here is, to chemists, the reaction is the system. We are the surroundings. right? So in coffee cup calorimetry, when we do a chemical reaction, so let's say a neutralization reaction, the reaction is the system, but typically what we're going to say is that the water is the surroundings. All right? This is what we're going to be doing constantly in this section, right? The reaction is the system, but the water is the surroundings. So when I have a thermometer in this cup, sitting in a coffee cup where a reaction is taking place, I'm measuring the temperature changes of the water. So I'm measuring the temperature changes of the what? The system or the surroundings? The surroundings, because I'm measuring the water, and that's super, super important, all right? So the sign for Q is very, very important in calorimetry. And honestly, before you even do any calculations, what you need to do is observe what happens in your chemical reaction. Use your intuition to get the sign of delta H before you even do any calculations, right? So now that you have like the big important detail in calorimetry, that your thermometer is sitting in the water, that thermometer is measuring the surroundings. So that means if your thermometer records a temperature increase, your surroundings is gaining energy, heat. Where does that energy come from? The reaction. So what is the sign of delta H? Negative. It's really weird, okay? That you're going to go to lab, you're going to see the thermometer go up, but you're going to calculate a negative quantity at the very end. And it's weird. It messes with our brains. But you got to get used to it, that your thermometer is measuring the surroundings, all right? So if we record a thermometer temperature decrease, what does that mean? The reaction did what to the heat? It absorbed it. So the sign of delta H is positive. It is an endothermic process, all right? So that's very, very important, all right? So let's do a demo here, all right? So instead of heat and explosions, let's think about our reaction and our system, but using light instead. Light is a source of energy as well. So let's do this demo again and tell me the light energy in this reaction, is it being gained by the system or is it leaving the system? So we did this one before. All right. So tell me, this thing is what? The system or the surroundings? It's the what? Okay, this reaction that I'm about to do right now, it is the reaction, it's the system, so therefore you are the surroundings. Yeah, so tell me, energy is being transferred how? Ooh. Okay, which way is energy going? In this reaction, light is energy. So is energy, light, entering the system, the reaction, or is it leaving the reaction? Leaving. So what is the sign of delta H or energy change in this reaction? Negative, yes, because light left the reaction. So what do you think I'm going to do next? I'm going to do another one, yes. So here, light left the reaction. Where's my Apple Pencil? Oh, I need to clean that. So this one, yes, it is a negative sign because energy is leaving the reaction and it's entering you. We are the surroundings. So the next one that I'm going to do here is a different reaction. It's a different reaction. Well, hopefully it's going to be the other way. Okay, so in this reaction, we'll know it's a reaction by a color change. So this is how the reaction looks like normally, all right? And so what I'm going to do is shine some light on this same test tube. It's the same substance, but it's just going to be a little bit different. So it's starting off like this, all right? Sorry, is it already happening? I have to shine light on it. Okay. Shine light on it. Is it changing? Yes. No? It's not changing? Okay, well, I'm trying not to shine in people's eyes, I guess, with this thing. All right, did it change? Yes, it changed. So this chemical reaction happened after doing what with this light? What happened? What did the reaction do to this light source? Absorbs it, and see, look, now it's going back because like the light's off of it, but I can do it again, all right? Shine light on it again, and it should go back. So in this reaction, what is the sign of delta H? Positive, because it's doing what to the light? It's absorbing it. All right, so we'll pick up at calorimetry on Thursday. Yeah. Yes.
Do we need to memorize like the specific heat or the heat capacity equation?
Do we make you memorize like anything? No, we don't. Yeah, so, but you do need to know